Okay, let's get started. It's not that early. The rain has turned people into scaredy cats, I suppose. All right, so remember the last class I said there was a feature built into MATLAB that helps you look at a bunch of different systems. And I did a little bit of homework because I couldn't remember the name. And then the name came to me while I was driving home that day. So I just did a little bit of work. So let's go ahead and develop a transfer function. And remember, what we have to do is we have to do a numerator. And let's just call it a numerator value that's 1. And we do a denominator. And we'll do one of the systems that we had in class. We had s squared. Why is this putting up? We had s squared, which is 1. And then 2s. And then 9. Now we have to put that in transfer function mode or position. So we're going to do our system is going to be our transfer function, and we're going to pass it the numerator and the denominator. Okay, so that looks like one of the transfer functions we did, right? So now we have in MATLAB, in our workspace, we have an actual transfer function. So here's the key, the word or the built-in that you're going to type in. It's called LTI view, linear time invariant view. You're going to launch it. And again, this is only available to you if you have the control systems toolbox. It's going to give you this prompt, which is really helpful, right? It simplifies the analysis of linear time invariant systems. So if you are doing your homework and you have a linear time invariant system, I said, what's the percent overshoot? What's this? What's that? You can certainly use that. So I kept the help up just to show. Now, let's go ahead and maximize this. And I want to go ahead and import in a system. So you can either go from a script file or in our workspace, everybody see that we have the system in there. So if we import it, watch what happens. Watch with magic. There you go. It actually shows you what the output is of the system given a unit step, which is exactly what we were doing for the second part of our work. And here's the best part. Right click and look at the characteristics. Remember how we have to calculate peak time? It actually tells you what the peak time is, or shows you on the graph. Dylan. Step input, yeah. You could get the results, but I don't know if you could get your way backward. So what I would do is I would have to check my results to see what I would get. Okay. So you can see that the rise time, once we move our cursor over here, it actually tells you it rises, right? Or our peak time is 1.11 seconds. The percent overshoot is 32.9%. It's peak amplitude, et cetera, et cetera. That's part of it. So that's the peak time. You also can do rise time, which we already know goes from 10 to 90%. So it'll calculate that value. And again, you can hover over here and it tells you how long. Then we can go to settling time. You can just add all these ones. And here's where we have to look a little bit. We have to hover on here and we see that our settling time, when it's within the 2% of steady state, it takes about 3.7 seconds to do that. And then the last characteristic that you can display, whoops, takes 5 time constants to go ahead and reach steady state. Why is it displaying? Maybe it doesn't want to display. Let's try that again. I don't know where the transient time is. It's not showing up. I guess it's beyond the curve. You can't necessarily see it. But this is where it reaches its time in about 7 seconds is when it does that. Okay. So this is really good if you want to do a step response. You also can do impulse, initial condition, and there are more things when we start to do it, root locus and Bodie and all that stuff, we can actually see that. Okay. So really, really quick and dirty way to check your results and see what you're getting. All right. Nice little built-in feature to MATLAB. Questions on that? I know you're not all that impressed, but I think it's kind of cool. Works pretty well, right? And you can model different systems, right? So if we want to add another system, what was the case when we had a critically damped system? Do y'all remember? The only thing that changed was our denominator. This was a 6, right? Because that's a perfect square. So if we do it again, we'll call this system 1, just so we won't overwrite it. Now we'll go back into here and we'll import system 1. Move this down here. Now you can see the second system. And it's displaying all that same information. Okay? Except there is no percent overshoot, right? So you can't see percent overshoot here because it doesn't overshoot. So there is no peak time, et cetera, et cetera. So if you wanted to monkey with things and change things around, you can actually view those characteristics pretty easily, I think. Any questions on LTI view? Okay. Well, let's get into the presentation. Where is the presentation? It was up. There it is. And we're going to do some block diagram math, but we're going to show everything as blocks and combine them and do whatever we need to do. I want to wake up. Sorry, it's thinking awfully hard. Okay, so here is our block diagram model, and we're going to pretty much work with block diagram representations of systems. And the reason why we do that typically is it doesn't really make a lot of effort, or it doesn't really reduce our time if we use those ones on the right, which are our signal flow graphs, which eventually just converts our boxes into arrows. Okay, and then the arrows would normally go to the right or to the left, depending on the direction. You see some signal flow graph, particularly when you do Mason's gain formula. We're probably not going to cover Mason's gain formula in this class because there are much easier ways to do it. But here's the key thing. This is a transfer function for a very simple system, an RC circuit, right? It could be an actuator for a motor. It doesn't necessarily matter, but we can come up with a really simple representation of one part of our system. And then we're going to take those and add those together. So I'm looking at the RC circuit. I'm looking at the RL circuit. I'm looking at the LC circuit. And each one of those inputs to those elements is going to go ahead and affect the output. So I figure out each of these individual block or gains of each of those systems. And then I go ahead and add them, subtract them, do whatever I need to do. So the first one we'll do is we're going to have parallel blocks, and we're going to have all 3 of these blocks. So we're running an input signal, and then on the output, they're going to be summed together. Can you think of an application that would work really well for that? Oop, can't draw straight. How about the input to an inverting op-amp? All 3 of these are going to have a current going through here. And what's going to go here is the sum of those, right? Okay. So they say that the blocks are in parallel with each other, but we're just treating them as the summation because of the summing block here. All right. And again, we don't want 3 individual blocks. We want an overall representation of our system so that we can perhaps simplify the system down. So here's the output of each of those individual blocks. Remember what C needs to be equal to. It needs to be R times G1 plus R times G2 plus R times G3. So from an equivalence perspective, R is coming in to one block, and what comes out should be RG1 plus RG2 plus RG3. So this here is going to be the equivalent gain of the 3 of those. Well, hopefully what you see is just the summation of those 3. right? So we sum those three together. And our new block representation is just here. We got rid of the summing junction. We got rid of the three individual gain blocks. And boom, we have a parallel or the summing junction values. Very simple, very efficient, very easy. Any questions on adding whatever, putting in as many of them that we need to in parallel? Generally is a pretty easy one. In series, remember what our output needs to be is G1 times G2 times R. So from an equivalency perspective, where I'm putting these two blocks in one block, my G equivalent needs to be those two, right? Multiplied together. So easy peasy, right? The equivalency there means our input is R, our output is C, and inside our block, our single block now is G1 times G2. What about feedback? Feedback is taking the output, whatever the output happens to be, and then running that back into the system, into a summing junction, and normally subtracting the feedback value from the input. And the reason why we do that is because we want to calculate the error, right? So this is our set point. We want this to be at whatever value it is. What we get back may or may not be the same thing as our set point. So the difference between the two is the error that we get. And so let's go ahead and do the block diagram here so you can see. We'll call this the error signal. So our C of S is just going to be equal to our error times our G of S. It's not equal to R, right? This is not R. It is E. It's the error. So now what is coming back? It's just C times H. So my error signal is equal to my input, R, subtracting from it the fedback value, C times H. Now I can go ahead and substitute that in there, and I've got C of S equals R minus CHGS. I got to do a little bit of factoring. So I've got my RG, I've got my C over here. I'm looking for a transfer function of C over R. So I'm going to move the C term to the other side. Everybody see how I did that? I just added it and then factored it out. And then I'm ready to find my transfer function. So for a feedback system with a gain in the feedback value of H here, and this is the most important block diagram that we're going to have. And the reason why it's the most important is most real world systems are going to be operated with some feedback. We talked about this, the temperature in this room, for example, right? Right now, the window is slightly open and the temperature is doing what it needs to do. But if somebody's cold, or if we're all cold, or if we're all hot, what are we going to do? We'll close the window, or we'll open the window more depending on what the conditions are. So we are closing the feedback network to make that work. This is a terrible feedback system, right? We should all be fired because the heat is coming out of there. And because we crack open the window, we didn't crack open the window. The window's been open for who knows how long. That's just wasting energy going back up. So if you were in a process, if you're in an industrial facility and you had a system that was cranking out heat and your solution was to just dump the heat into the atmosphere, that would be a waste of energy. That would not be a good process. So how would we improve our process? Have different outfits depending on the room. You can change your outfit if you need a pair of shorts and a tank top, or if you need, a snowsuit of some sort. You just decide on what you need. It's not a good solution, right? Because again, that requires you to monkey with the input, and the input is unpredictable, right? So we only can modify that G. And what we're going to find is we're going to add a controller to the plant. So the plant is the room dynamics. The controller is whatever is telling that thing to open the valve up, close the valve up, et cetera, et cetera. And then we can only really use a controller. We only really should use a controller at such time when we're feeding back what the output is. It doesn't make sense to have a controller if we have no way of knowing what the output is. What's the point of controlling something if we don't know what it is? So if it's an open loop system, you don't bother putting a controller. If it's a closed loop system, you do. And you've talked about this a number of times, I believe. Who here has taken Jude's PLC class? Everybody? What is one of the controllers that she probably talks about fairly regularly, more towards the end of the semester? That's the actual piece of equipment, right? But the actual controller that's built into the Slick 500 software should be a proportional plus integral plus derivative control. Does she ever talk about PID or PI control? Never? Oh, everybody's looking at me. Okay, well, she used to talk about it. But the idea is that you need to add some intelligence. And so, well, in your PLC class, do you use analog inputs and outputs ever? Or is it all discrete? So you do use analog. Okay. So that's a good thing, which is an analog input is maybe, I don't know, it's the speed of the motor. If the speed of the motor is not, what's that? So it's monitoring something in the room, right? But what if you weren't satisfied with the results? What if the relative humidity in there is 100%? Wouldn't be the most comfortable room, right? So you'd have to have, yeah, it'd be terrible. You have to have a plant which incorporates some sort of either dehumidifier or humidification system that can bring that temperature to a lot better value. Knowing the relative humidity in there, how useful is that is if you can't do anything with it? Not much, right? So do you remember the cookie lab that we did? When the relative humidity was high, you had more moisture content in the dough, and you needed to bake the cookies for a longer period of time, right? To get the moisture out of the dough. And so what we did is we had a very simple basic controller that would speed up or slow down. But a better application if you're monitoring it, and that's really most likely what the PLC stuff is built for. I'm monitoring relative humidity, and maybe I need to track it from an enunciation perspective. But if I have an analog capability, I'm going to go ahead and probably try to control that. What would be another application when you're saying, hey, relative humidity, I'm monitoring it? Maybe alarm, right? So if I'm only alarming, I probably wouldn't run a fancy-dancy analog signal back to the PLC controller. I'd buy a module that sits on the wall and monitors relative humidity, and then I'll set it if it's above 50%, I'll just send an alarm input to the PLC. So that is just one simple discrete contact. I don't have to run a 4 to 20 milliamp loop. Is that what she runs in there, 4 to 20s, which is actually what the industry standard is. So even though they have fiber optic and can do it really cheaply with communication, they still like 4 to 20. But the idea is that why not just run a discrete on-off type thing if it's above or below a certain set point? So alarm would be one thing. But if you're trying to get actual indication, why do I need actual indication of what the actual relative humidity is unless I'm going to do something with it? So that's where you get into the more controls. And that's what we're talking about here is modifying your controller. So here's our final block diagram. Our input, C output, and here's our block representation, our equivalent circuit. All right, now we're going to move stuff. This is a little harder. And moving a summing junction is we see that we've got an R and an X. Our input is ultimately R, but our X could be someplace in the control system. We don't necessarily know about it. And the C is that value. So let's walk through. The output of G of S is R times G. My C of S, the output of this particular block, is RG, and then you just do plus or minus X. Now, if I want to move the summing junction in front, what do I need to do? Well, I still have R going in and X going in, but does this here match that? Are they the same? No. G is being multiplied, or X is being multiplied by G. So how do you suggest we make it so that those two are equivalent to each other? What would you do? What do you suggest? This one has a multiple of 1 over here. This one has G. How would you make sure that the second term, because we've modified it, right? How do we make sure that that second term is going to be the same as the first? How about I take my X and multiply by 1 over G? Because then this is equal to X over G. And when I run it into the summing junction, the G that gets multiplied over here gets divided out. And so I don't actually have a G term there. So here's my modification. And that's how I replicate that. And we'll see why we need to move summing junctions at a later date and time. This is moving a summing block or summing junction forward. Now we're going to move it backward. So take a look. This is R plus or minus X. The output is R plus or minus X times G. If we modify that so that we have our summing junction is downstream of this X block, we can clearly see that this is R times G, which meets this one over here, right? But if I just ran my X input into here, then I would not have the G multiplier over here. So I multiply. So here's the key thing about moving summing junctions. If you move to the left, so moving to the left, you're moving your summing junction to the left, divide by gain. If you move to the right, multiply by the gain. Okay? Really, really important to know which way you're going. Left, right, because sometimes you divide, sometimes you have to multiply. Now, a summing junction is different than moving a pickoff point, okay? If I want to move my pickoff point to the other side of G, I see that my C term is equal to R times G. If I'm on the other side of the pickoff point, C and R would be the same, correct? But clearly, C is not the same as R over here. I've got to multiply by G. So what do I need to do? Just multiply by my G block. Okay? So does anybody see why moving a summing junction is different than moving a pickoff point? Because before, we said moving left, you divide by the gain. And moving right, you multiply by the gain. Over here, when we move the pickoff point to the left, we have to multiply by the gain. Okay? Yes, sir.
Why?
Great question. So the question is, why would you move the pickoff point? Why don't you just pick off the point wherever you want? Great question. Anybody have an answer? You don't have that option, exactly. The real life is you walked up to a system and it's built. The pickoff point is based on how the system is fabricated or designed or constructed, whatever you want to call it. So this pickoff point is not your ability to do it. You've walked up to a system and that pickoff point is there. You're feeding back from that point. Whoever designed the system said, I need to feed that back to get the result that I want. So I can't just say, oh, I'm going to pick off this point and run it to the gain, because that doesn't replicate the real world system. Okay, so you have no choice. But you, as the engineer, have to be able to analyze a system, which means, all right, here's my actual system. Now I need to analyze it. And a system with a pickoff point shown as originally designed, I can't simplify it down. Over here, if I move it, I might be able to simplify that system down and get better results. That's the reason why you do it. So go the other direction, move the pickoff point to the right. What do you think you're going to need to do? Don't even skip ahead. If we move it to the right, we have to
divide.
Divide, very good. Same thing. Okay. Move to the left, multiply. Move to the right, divide. So I don't know if this is going to confuse you, but move left, multiply. Move right. We will divide. But that's only for pickoff points, not summing junctions, okay? It's the opposite for summing junctions. And here is a figure. And for your next test, I'll provide this to you because it's really hard to do these. So it tells you what's being done. So you can either do this one of two ways. You can look at what you need to do, which is what manipulation you need to perform. I need to combine blocks and cascade. I need to move a pickoff point behind a block. I need to move a summing point behind a block, whatever I need to do. Or you can look at it pictorially and you can say, oh, I've got this system that looks like this and I want to make an equivalent. So, you know, whatever works best for you. And then the output of what your equivalent is going to be shown there. Okay. So combining blocks. Then we do the parallel where we do them in parallel, and we only show two, right? But you can do this for 2 million, it doesn't matter. So the first two are pretty simple. The item number 3 is moving our pickoff point. So you can see we move our pickoff point from right to from left to right, and we have to divide. Next case is we do the opposite direction. We move the pickoff point from right to left, and we have to multiply. And then our summing junction. If we have a summing junction, we move our summing junction so that we have our gain. We have to multiply the input. And then the other one is moving it in the opposite direction. We have to divide by, okay? So these are opposite, right? You can see when I go from here to here, I divide. But when I divide, I actually move my summing junction from the other side to over here. And you can see I get the division, okay? And then the output equations are just showing you what the transfer function. So this is the G equivalent on all these. Let's see right here. Yeah, so you can see the G equivalent there. The one that I didn't include in this table is the one with feedback. Because feedback is so important that you need to know how to do it. That's just one you have to practice and learn how to do it a number of times. Okay, so here's our block diagram. This is our real world system. We have an input and then we get an output as shown. Somebody, some smart person has gone through and helped us out to figure out what the individual pieces of the system are modeled as. And we're told to find G equivalent. Because maybe we need to go ahead and add in some performance characteristics. We need to tweak something. All right, so we need to simplify this down. Is there anything that you think that we can simplify this down? Well, if we move this summing junction over here, does that help us at all? Does that help us at all? A little bit. It might mean that we got a bigger path. How about moving this summing junction? We could do that. That helps us a little bit. But if we move this pickoff point here, right? Because that pickoff point, this here is a feedback path, isn't it? But the problem is we've got a pickoff point here in the middle of our feedback path or our feedback loop, which means if we tried to do this as a feedback path, that pickoff point would no longer be valid. So the preferred thing to do is to get that pickoff point out of there. Now, can I move the pickoff point over here? It's possible, but it's a lot of work. It's usually better to move something one item away. This one, you'd have to move it 2 items away, right? So it's much easier to move that pickoff point to the right, because now these are all, this is just a common node, right? So if I move that to the right, I can have a pickoff point here or here, it doesn't matter, because it doesn't affect what's inside that feedback path. So I'm gonna move the pickoff point H2 to the right. So move the pickoff point, moving it from left to right. Remember, from here, it's not being multiplied by G4. So I'm moving left to right, which means if I go to my table, right, when I move a pickoff point, what do I need to do? I need to divide by whatever that game block is. So I divide that game block. Now, why not I combine that into one feedback path, right? Make it simple. Combine that into just a feedback block, because that's really simple. So, and then, well, actually, we can cascade these two. That's a pretty simple one. We can do those in cascade. So I didn't even add that as a step. Now we're going to collapse the inner feedback loop, which is here. And this is got to be careful. This is positive feedback, not negative feedback. So when we had a negative feedback, we had G over 1 plus GH. Negative feedback is G over 1 minus GH, okay? So just be careful about the pluses and the minuses. So we cascade those two together, G3, G4. Now we only have a G and an H, and we can combine those really simply there. Okay? Questions on that? Dylan? The which block? Right here? I didn't move the G4 block. I moved the pickoff point, right? So I'm not actually moving a block. I'm just picking this line, this point right here, and moving it to the other side of the block. So the block doesn't disappear. It stays there, but where I take off from our block diagram is from the right. Okay? Sort of kind of makes sense. Just think of what I'm doing, right? Go back to your table. All I'm doing is moving the pickoff point. I'm not getting rid of G4. So I don't touch G4. G4 stays there, right? That's not my step one. I'm just moving my pickoff point. That goes there. And by going back to the table, moving a pickoff point from left to right means I need to divide by the block that I'm moving around. Then I put H2 and 1 over G4 in cascade. Now I'm ready to combine the inner feedback path. So I'm going to do G3 and G4 in cascade. Now I can go ahead and do positive feedback, and I can combine that. What would be the next basic simple step that you would do to this one? What would you suggest? G2, yeah, put G2, G3, G4 over 1 minus G3, G4, H1, put those in cascade. That's our first step. Now we have a feedback path. It's going in this direction, right? It's going up, but it's still a feedback path. It doesn't need to go down. It's still bringing that value and bringing it back. So let's go ahead and collapse that. So this here is my G, and this is my H. And this is where things get a little hairy. Why do they get hairy? Because look how complicated they get. Do you remember about a month ago or so when I said you should learn to love to do simplification with fractions and fractions? Can you see why? They get busy really quickly. But if you're really good at algebra, that's not too bad, right? Everybody want to try to go from this to this? Want to see the practice? No? Yes? Who wants to see it done? Because you all should be able to do this. I'll show you, or I'll try to show you. Press whiteboard, closed. Zoom just quit on me this morning too. Does anybody hear that campus is maybe switching to Teams? I've heard a couple rumblings because Teams has got way more power, and that's what people use in the industry. Like when you graduate, the likelihood of you using Zoom is pretty low, I guess. But Teams is being used a lot because you can track and you can assign and you can do all different things. I guess if you want a really basic, like what we're using Zoom for is pretty simple and basic. You can do a lot more in Zoom. But for academics, right, we're just sharing information and chatting. We can do polls. But in Teams, you can actually assign people work tasks and they can check things off. I mean, it's a way, it's becoming more of a workflow process management tool. So that's why you're starting to hear more about Teams. Some people even use WebEx, but WebEx is more like Zoom. It doesn't have quite the power that Teams is. Yeah, but that just means you just have more licenses, right? I mean, that's, and you can do team meetings. You can do those. You host it all online. You don't actually have to have the Teams client installed on your machine. So I've been to meetings where you've had large groups of people, maybe 50 people. I've never done a WebEx meeting where they've had thousands of people. And it might be that the server on Teams isn't built up for that yet. Is it? But that's, like I said, that's probably just a simple limitation in terms of what the server can handle. But what is power used for management?
Except for company-wide meeting. WebEx.
That's WebEx. Yeah,
It's
because
the only with my.
yeah. Anybody else use WebEx or Zoom? The work world? What's that?
I use WebEx.
Right. Yeah, WebEx is great because it's a pretty simple, basic, easy to use. But Teams has got way more capability and power. It's harder to use, obviously, right? But yeah, WebEx and Zoom are almost the same. Zoom is just really easy to use. All right, so let's go ahead and multiply this out. So I'm going to go ahead and put G2, G3, G4, all over 1 minus G3, G4, H1, all over. Now I got to put this under a common denominator, right? So my common denominator here is going to be 1 minus G3, G4, H1 times G4 plus G2, G3, G4, H2, all over 1 minus G3, G4, H1, and then that's times G4, right? Gotta be really careful about keeping track of parentheses because you can mess things up pretty easily. So now I'm going to invert and multiply. And what I'm left with is you can hopefully see that this term here will cancel with that term. And I've got G2, G3, G4, G4 all over 1 minus G3, G4, H1 times G4 plus G2, G3, G4, H2. Everybody okay with that? I can see that G4 is common to both terms. So that means I can cancel one of those out, right? And then what I have is G2, G3, G4, all over 1 minus G3, G4, H1 plus G2, G3, H2. Any more simplification can be done here? Yeah, very good. I can get rid of G3. Oh, no, I can't get rid of G3 because I don't have a G3 over there, right? So I'm pretty much stuck here if I don't want fractions in my fractions. So let's take a look at our work, G2, G3, G4. That's what we have in the numerator. In the denominator, 1 minus G3, G4, H1 plus G2, G3, H2. How'd we do? A for the day. What's that? Quit while you're ahead. Was this too hard? Too challenging? You can say yes. What part would have been difficult? Starting? Yeah, they do take a while. And so the only way that I can say to simplify it is you always, your denominator, you want to put that under a common denominator. So start, and that's exactly what I did. I put this denominator under a common, I put the denominator terms under a common denominator, and then I inverted and multiplied. That's the only way to get rid of fractions within fractions. And because I kept all the expressions, I could see that things canceled out pretty easy, right? Like you can see that these terms cancel out, and then you just have to be meticulous, right? I've got a G4 term that I got to keep up there, and I've got G4s over here. This is the hardest step. This, we'll call that step 1. That's the hardest step. After that, the steps are pretty simple. Hopefully you see. All right, so now I'm going to do a cascade, right? Put those in cascade. Now I just have a regular feedback path. There you go. How about 5 minutes? You do this one. Well, it is when I do this. It's funny, but why do I do this? Because over here, I can get the denominator. And what do we say about the denominator? The denominator is what determines the performance of our system. If I went all the way back to the beginning with all these blocks, I'm like, all right, well, how do I start? But from here, by looking at the denominator, once I plug in the actual G's and the H's, then the hope is that you see that it results in, you can actually model the system and do something with it. Does anybody want to try this for fun? I can make it even easier for you. This part right here is going to end up right over here, right in the numerator. And then that term cancels that term out. So you have G1, G2, G3, G4, all over, and I'll just call this, we'll call it G325, just to make it easy. Right? Plus G1, G2, G3, G4 times H3. Everybody agree with that? When we've just inverted and multiplied. Now we have to see if any of this stuff is going to be in common. And you can see because I have a 1 minus over here, there's really nothing I can do. I can't cancel any of these terms out. So that's my final value. That's what I'm going to get. So this term right here is G325. This term and this term are the same. Those are the same. So if you wanted to save yourself some time, just by recognizing that that denominator is going to end up in the numerator, you get the result you want. Okay? Questions on how to do that? Because now I can do something with the system. Now I can analyze it. You also can do this in MATLAB, but I don't suggest it because you can do symbolically and you can do the process. We won't get into that. All right, 5 minutes. You want to try it or you want to do it together? You want to try it? Do it over in whiteboard here. Give it a whirl. Remember the rules or the mottos. What do we want to do? We want to only move one item. You see, moving one item, it makes it a lot easier. Which one? H1? Yeah, usually feedbacks are H's and feed forwards are G's. And if anybody wants, I could also bring up the table, now that everybody has this written down. Do you want me to bring up the table to figure out, would that be helpful? Is everybody ready that I can do that quickly? Few seconds? Good? All right, so let's kill this because it would take a lot of stepping back to go through. Come on, let's get there. Here we go. I'll maximize this so you all can see, hopefully. All right, so now you have that. Take a look at the table here. Which would you use to simplify our in-class example? Move the pickoff point for H1. Let's go back to the diagram if that's okay. So what Noah has suggested is the pickoff point going into block 1 should be moved. Everybody agree with that? Anybody disagree? Should we move to the left or to the right? Right, you can go either way. Move it to the right. You get two options. You can go here, whoops, here, or here. Which way should we move it? To the right?
Well,
Everybody okay with that?
I think we should move it to the left and
Two people said to the left. So folks who said to the right, why would you move it to the right? Yep, you can certainly combine G1 and G2. But does that really save you any time? Because you still have a pickoff point that's on the other side of the summing junction. So don't I need to still do some work? If I move it to the left, it's over here, right? And it might be a little weird to say, hey, take the input and then subtract from it the input times H1. But, you know, we're just doing the math part. So my suggestion would be to move it to the left. All right, move it to the left and let's see what you get. If you want to move it to the right, that's fine. You'll just need an extra step to move the summing junction too. That's another good thing to think about these things. I'm never moving blocks. I'm only moving pickup points or summing junctions. Never touch a block. Pardon? Oh yeah, absolutely. Yep. Have you decided which one you're going to do? Is it item 1, 2, 3, 4, 5, or 6? Well, pretty quickly, if you just look at the description, we're talking about moving a pickoff point, right? So it should be either 3 or 4. So which one is it? Are you doing 3 or 4? 4, right? You're moving the pickoff point from the right to the left, which is another way of saying moving a pickoff point ahead of a block. So what you should do, we'll keep this as a summer. This here is our feedback path. And now my pickoff point is over here. But I need to multiply that by G1 per the table. And now I'm not changing anything that's inside my summing junction. This is plus and minus. Now what should you do? Yeah, I would cascade G1 and G2. Are you all okay if I cascade H1 and G1 as well? Everybody okay with that? An ugly looking summing junction. Now what should I do? So there's a suggestion of moving the summing junction that's between G1, G2, and G3 and move it. I called it summing junction, and then I wrote G3 here. That's not very bright. Anybody agree with Avery? Anybody disagree with her? Avery's smiling. Does that mean you disagree with yourself? I have maybe a slightly different perspective. How about if we change this line a little bit and just do it over here? That's okay, right? And don't I have a feedback path here? And don't I have parallel path here? There's no reason to move the summing junction because it's just a parallel path. So which one do you want to do first? The feedback path or the paralleling path that we have forward? Your choice. Doesn't matter. Feedback? Okay. So remember the feedback. We don't have that in the table. The feedback is, if it's negative feedback, is 1 over GH. H, we can see, is equal to H1 times G1. What does G equal?
would it be?
Oh, sorry, Branson. Go ahead.
I was gonna say RS.
No, it's not, because RS is an input signal.
Okay.
RS gets multiplied by whatever block is there. If there's no block indicated, that's the same thing as saying, take that signal that's coming in and just passing it through. Multiply by 1. That's all that means. Okay. So this becomes, so G, which is 1, over 1 plus GH. Now, I have my next summing junction. Now what should you do? The what? Yeah, let's do this second one. We don't want to do the cascade of the other ones because we still have that parallel path. So let's go ahead and keep this in here. 1 over 1 plus H1 G1. And then this is just going to simply be the two gains added together, right? And now I just have 3 in cascade. So my overall block diagram is now going to be G1, G2 plus 1. All of that times G3. All over 1 plus H1 G1. Just multiply the numerators and multiply the denominators. If you're not sure, remember these are just divided by 1. And so my equivalent G is equal to G1, G2 plus 1. Multiply that by G3. All over 1 plus H1 G1. And with this system, I can do a lot. I can analyze this system. I can do, I can do LTI viewer for this. I can do all that different stuff. If you have Simulink, you don't necessarily need to do all this work because Simulink, can put signals together. But if you're trying to do some design parameters, sometimes it's a lot easier to do that. Questions on that? Hard, easy, medium? Get more progress or practice? Yes. I will provide that for you. Yep. And if people want to do practice, you're certainly welcome to do what everybody suggested at the beginning of class, or some people, I should say, which is to move that over here, which is fine, but then you still have to move that over here. So you have 2 steps that you need to do before you can really start to simplify things down. Okay, which is fine. You can do that and you should end up with the same result, but it just might be a little more work. So whatever you want to do, it's up to you. All right, let's get down to the right spot here. How about this one? What would you do here? Anything? This one's actually pretty easy. I've got a feedback path here. I combine that. Then I combine that. Then I combine that. And then I cascade it with that. So let's do that one. All right, so we'll go ahead and well, I guess we'll have to draw it all out. Here's G1. Here's a summer. Here's a summer. Now I'm going to replace this with one path. So this becomes G2, G3 over 1 plus G2, G3, H1. And then I've got H2 going over here. And I have H3 going over here. Now this is where it gets a little tricky because now I got a bunch of math. So this one is going to be equal to, and I'm going to just do it over here because it's going to be a little bit of algebra. So G2, G3 over 1 plus G2, G3, H1. That's the feed forward gain, right? That's all over 1 plus G2, G3 over 1 plus G2, G3, H1 times H2, correct? Fractions within fractions means I have to do this. And if you allow me to do this and tell me if I go too quickly, I'm gonna go ahead and do a common denominator and invert and multiply. My common denominator is that. And then I invert it, so I end up with 1 plus G2, G3, H1, plus G2, G3, H2. Everybody see what I did there? I just did common denominator and inverted and multiplied. I did it all in one step. Right? This part over here goes up over here. And then when I invert it, I end up with that term there. I cancel those out, and that becomes G2, G3, all over 1 plus G2, G3, H1, plus G2, G3, H2. So now I've got one more. Here's G1. Here's my summer. Here's that big ugly thing that we just calculated. Now I only have one more feedback path to go. And that is, we'll just call that GA for lack of a better term. And now we're going to combine that all into one group. So this whole thing is going to be combined. And it's going to be G2, G3, over 1 plus G2, G3, H1, plus G2, G3, H2, all over 1 plus that, times H. And I'll move my H3 up here. Oh. Okay. Do the same thing I did before. Common denominator, invert, multiply. Then that becomes plus G2, G3, H3. And then I multiply it by what was there in the numerator originally. Okay. Those cancel out. And then I'm left with G2, G3 over 1 plus G2, G3, H1, plus G2, G3, oops. H2 plus G2, G3, H3. And that we'll say is equal to G sub B. And so my final little piece is G1 times GB. Those two are in cascade. So what I end up with is G1, G2, G3, all over 1 plus G2, G3, H1, plus G2, G3, H2, plus G2, G3, H3. And this here is our final block. Yes, sir. Yes, I'll just say yes. Oh,
If we define something, GA or GB, like we did, is it okay to express our time in certain terms of, like GA or GB, as long as it's not defined?
you can just be careful, right? Because if you noticed over here, when I put GA in here, right? The GA in here has some stuff that will cancel out, right? So if you just wrote this as GA over 1 plus GA times H3, you don't get to see where a lot of that stuff cancels. So it might be like a lot of work. You can do it at the end. You can substitute that all in and do it all at once if you want to cancel things out. That just might be more confusing for you. So that's totally up to you. And the only reason why I'm being difficult about it is because I really need to know what that denominator looks like. I need to have that denominator, right? No, you can do it, but as long as you give me a denominator that looks like that, that's what I care about. burnt out yet? Well, that wasn't too bad. All right, well, why don't I, been doing this for a while. Why don't I let you guys try this one at home? This is a pretty easy one, and it give you an opportunity to do a little bit of math. Not crazy amounts of math, but a little bit of math. Questions? You got a lot of stuff to practice if you want, right? You can go play with the LTI viewer. The lab that you did yesterday, you can try doing that with LTI viewer. You don't even need to run Simulink. You can see what the results are. And then see if you get comparable results. And then you can just practice this. How about anybody from TV land? Any questions?
Are you gonna post these slides?
Yes, I will post them right after class. Any other questions or comments? When we get back on Tuesday from break, we'll actually spend some time working through these, coming up with stuff, so. All right, well, if there's nothing else, have a wonderful day and weekend. And I'll see you all on either Monday or Tuesday, whatever day. Take care, everyone.
Thank you, Paul.
Thank you, Paul.
Thank you.